Hi everybody, hope you're all having a good day today so far. Today we're going to talk about continuity of the budget set correspondence. We're going to determine whether the correspondence is closed, whether it's upper hemicontinuous, and whether it's lower hemicontinuous. So let's start right in. Let's write down beta for the name of our correspondence. It's going to go from the unit simplex into RL plus, as we described in the previous lecture, and it's actually going to be the case that everything we're going to do would work just as well today if we take the domain of the budget set correspondence to be all non-negative prices except for the zero price list where all the prices are zero. So either one of those betas will work, although we'll actually use this when we have to make a distinction. And of course, the budget set correspondence picks out as the image set at any P, the budget set, which is the set of all points or the set of all bundles, such that P dot X less than or equal to P dot X circle. That is all the bundles that satisfy the budget constraint, where, as we said last time, X circle is the bundle, the initial bundle that the consumer owns. Let's start off with the simplest of the three results, theorems, that we're going to do today, and that is that the correspondence is closed. So it's a closed correspondence. And so let's write down what that means here. To say the correspondence is a closed correspondence means that the graph of the correspondence is a closed set in the product of the domain and the target space where the graph lives. And to say a set's closed, of course, is to say that if we have points, if we have a sequence of points, and all of those points are in the set, so in the graph of beta, for all n in n, let's say, and if that sequence converges to a limit, then the limit has to be in the set as well. So that's just restating the definition of a closed set applied to the set, which is the graph of the correspondence. So let's see if we can give a proof of this theorem. And for that, let's actually, say this statement is 1. Let's say this statement here is 2. And this statement here is 3. So what we need to do is we need to show that 1 and 2 together imply 3. So let's first look at statement 1, and let's rewrite that in a way that will be useful for the proof. Let's say that Pn and Xn, this pair in this graph, means that Xn is in the budget set at P for all n. In fact, I should have had here Pn, and that says that Pn dot Xn is less than or equal to Pn dot X circle. That's the definition of the budget set. And that we could say, well, on the right-hand side, well, on both sides, we have real numbers. So this is a this is the dot product of Pn and Xn is a real number. Pn dot X circle, real number. So what we have now is a sequence of real numbers here on each side. And it will be easier to see what's going on if we get a fixed real number on the right-hand side. So what I'm going to do is I'm in effect going to subtract off the X circle, Pn dot X circle, from each side. So we'll have Pn dot Xn minus X circle is less than or equal to the real number 0. So we've just subtracted off this from each side. So this is what we now have on the left-hand side. So now we have a sequence of real numbers on the left-hand side, and every term in the sequence is less than or equal to 0. Let's look at our second statement up here. This says that the sequence Pn Xn converges to P bar X bar, and that's to say that Pn converges to P bar and Xn converges to X bar. And if that's the case, then we have Pn dot Xn goes to P bar dot X bar, just combining these, and we have Pn dot X circle goes to P bar dot X circle. And so now we have this sequence here and this sequence here, and if I term by term subtract the terms of this sequence from the terms of this sequence, I've got this sequence here. So let's do that. We have Pn dot Xn minus X circle, and that must converge to, taking this limit from this limit, that must converge to P bar dot X bar minus X circle. And so, since every term of this sequence is less than or equal to 0, it has to be the case that the limit is less than or equal to 0. So therefore we have P bar dot X bar minus X circle less than or equal to 0. And that completes the proof. And now you might say, well, wait a minute. We're supposed to prove statement 3 up here, and that doesn't really look like statement 3. But let's notice that this is P bar dot X bar is less than or equal to P bar dot X circle. And that's saying that X bar is in beta of P bar. So X bar is in beta of P bar, that is, X bar is in the budget set for P bar, and that is the same as P bar X bar is an element of the graph of beta. And that is what we wanted to prove. So we really have completed the proof. Indeed, it was a simple proof, just take a few moments. And so now we'll take this off and we will see whether the correspondence is upper hemicontinuous. So we'll take this off and then we'll be right back. Okay, let's see if we can show that the budget set correspondence is upper hemicontinuous. Let's write that down as a theorem. And the first thing we need to do, of course, is to remind ourselves what it means for a correspondence to be upper hemicontinuous. Let's put that over here. Beta being upper hemicontinuous means that if the budget set at a particular price list in the domain is a subset of some open set, so V has to be open, some open set in the target space, then there has to be an open set in the domain which is a neighborhood of P bar, so it's an open set that contains P bar, and such that for any price list in that neighborhood, the budget set at that price list will also be a subset of the open set V in the target space. So that's what we mean by a correspondence being upper hemicontinuous. So let's see if we can give a proof of this, and this is really going to just be an outline of the proof. I'm not going to go through all of the algebraic calculations that we need to do, but we'll set things up so that you could do those algebraic calculations. So, of course, we want to start off the proof by saying, suppose that we have a price list P bar at which beta of P bar is a subset of an open set. So we'll say, let's suppose that beta P bar is indeed a subset of an open set V. And so let's draw a picture of this. And of course, we'll draw this in two dimensions, meaning two goods, and in the domain, the price lists have two components because there's two prices. So here's the commodity space, the target space, and that's R2 plus in the picture, more generally RL plus. So we are going to first do this for price lists in the interior of the simplex, price lists for which all of the prices are strictly positive, no zero prices. So let's say P bar is in the interior of the unit simplex, which means that for all the components of the price list, all the components of the price list are positive. And of course, if all the prices are positive, then we know that the budget set is going to look something like this. That is, the budget constraint is going to be downward sloping, and in particular, it will intersect each of the axes. And the same thing will be true if there's more than two goods. There, the budget constraint, of course, will be a hyperplane, but that hyperplane will intersect each of the axes like this. It'll be a kind of downward sloping hyperplane. And so this is the budget set, so let's make a note of that. This is the budget set at the kind of benchmark price, P bar here. And so we need to find a neighborhood of P bar that will do what it says down here. And so let's start off by saying, well, I guess we haven't actually drawn the set V. So let's actually draw our open set V. And so let's take this squiggly line here, and let's say that everything below this squiggly line is the open set V. So the squiggly line itself is the boundary of that open set. And so the first thing now I'm going to do is I'm going to draw a line parallel to the budget constraint. And I'm drawing that line parallel to the budget constraint entirely below the boundary of V. That is, this pink line is itself entirely a subset of the open set V, just like the budget constraint. So then everything that we do is going to kind of turn on what we can do to keep things inside that pink bounded region. But the first question that comes up, first issue that comes up in the proof is, how do we know that we can do this? Let's point out that you've said that the line's parallel. Let's suppose that this is the initial bundle. I've used a little square for that. And so this pink line is parallel to the budget constraint, and that means that we could draw a line orthogonal or perpendicular to the budget constraint, which means that this line, this little line segment coming out here is simply a multiple of the price list P bar, because the price list P bar is a vector that's orthogonal to the budget constraint. Of course, it's not necessarily this one. It could be longer, it could be shorter. So this is really just alpha, some positive alpha, times P bar. And its length is going to be alpha times the norm of P bar. So that's the length of this little line segment here, this little arrow I've drawn. And I could do that anywhere along here because I've drawn this parallel to the budget constraint. Now, the first question that arises about this is, how can I be sure that I can actually draw this pink line that's parallel to the budget constraint, is away from the budget constraint, and is still inside the set V? Well, I guess you could say that's obvious that we can do this, because there's this great big space between this squiggly boundary of V and the budget constraint, so it's kind of obvious. I can draw a pink line here that's some distance away from the budget constraint. But what if the picture actually looked instead like this? Budget constraint here, and our our blue boundary of V here, maybe looking like this. So here, the distance between the budget constraint and the boundary of V is 0, even though the boundary of V might not coincide with the budget constraint. It might get arbitrarily close to the budget constraint, and then we actually couldn't draw this pink line some distance from here. That is, the alpha would have to be 0. The alpha, I couldn't have a positive alpha multiplied by this norm of P bar. So what guarantees that in fact I can do this? That we can actually put another line parallel to the budget constraint, or hyperplane parallel to the budget constraint, that's away from it, that's some distance away from it? Well, first thing, we're going to need a definition of distance between a pair of sets, and that's going to be something that will show up a couple or 3 times in the proof. So let's write that down here. We'll say that the distance between 2 sets A and B is defined, and this is a standard definition, is the infimum of the distances between any pair of points drawn from A and B. And so this is the distance between 2 sets. What we're saying here is that apparently the distance between the budget constraint and the boundary of V is positive. They're positive distance apart. It doesn't look like this, and that's what allows us to draw this pink line. And so how do I know that they are separated by some positive amount? And that is from this theorem, which tells us that for any two sets, A and B, that are disjoint, like the boundary of V here and the budget constraint, any two disjoint sets, non-empty of course, that are both closed and where at least one of them is bounded so that it's compact, then the distance between those two sets has to be positive, not zero. It has to be strictly positive. And of course, given the definition, given what we mean by the distance between sets, that means that there is a positive epsilon such that this distance between points in the two sets is always bigger than epsilon, greater than or equal to epsilon. So that notion of the distance between sets is going to show up again once or twice in the proof. But here, the way it shows up is that we want to use it to say that indeed we can do this construction of this pink bounded set here. And so to do that, what in our proof is going to play the role of the set A, and what's going to play the role of the set B in this theorem? Well, the A set, it says, is compact. Could have been either A or B, and I just chose A without loss of generality. So it seems pretty clear that the set here that's going to play the role of A is probably going to be beta of P bar, because that's obviously always going to be compact given that all the prices are positive so that the budget constraint's downward sloping. So that's going to be beta of P bar, the budget set at the benchmark price P bar, and what's going to play the role of B? Well, you might say the boundary of V, but actually it turns out, I think, to be a little more convenient for the way the proof's going to go, to say that the set that will play the role of B is the complement of V, V complement. So V complement is everything on or above the boundary of V. V is everything strictly below or away from the boundary. So the V complement is closed because V is an open set. We could say V complement is non-empty, I guess, because if V were all of RL plus, the proof would be done. So we'll assume that the set V here is not all of RL plus, or the interior of RL plus. So what plays the role of B in our theorem is the closed non-empty set V complement. And so the theorem tells us that those sets are separated, if you like, by a distance epsilon that is positive. And so in fact, we will even say that epsilon then will be this distance here. That's the Euclidean distance that they're separated, so I'm using the Euclidean norm here. So that's the distance between these two sets anywhere along here. And so now what we want to do is I want to actually define this point here as x hat 1. That's the intercept of the budget constraint with the x1 axis. And this is x2 hat, the intercept of the budget constraint with the x2 axis. And clearly I can do that for L goods just as well. So xi hat is the intersection between the budget constraint and the corresponding axis. And so notice that if I take this distance epsilon and I move beyond x hat by this distance epsilon, that's going to be about to here. So let's just write below that. That's the distance epsilon over here. And I can do the same thing over here. That would come to about there. This would be x1 hat, x2 hat plus epsilon. So this is the distance epsilon here. And notice, I have drawn this perhaps a little shorter than it is here. But notice that when I move out by the amount epsilon on any of the axes, that's not going to take me as far as the intersection of this pink line with the axis. It's clear that xi hat plus epsilon is a shorter distance than all the way out to here, because epsilon onto here is clearly less than the distance from here to here. So that tells me that if I go out from any one of these points on the axes, x1 hat, x2 hat, and so on, and plus a distance epsilon, I'm still going to be inside this pink bounded region, and therefore inside the open set V. And that's the key to the rest of the proof. So now let's construct a budget constraint that goes out to this intercept here and through the initial bundle. That budget constraint is a budget constraint for a different price list than the price list, the original price list P bar, and in particular, that price list has a lower price for the second good because we can afford more of it, and since we're in the simplex, it has a corresponding higher price for the first good, namely 1 minus the price of the second good. So here we have, I'm going to call this P2 hat. That's the price for the second good that generates this steeper budget constraint than this one, and that is clearly less than P2 bar. And we're going to do the same now for P1 hat. We're going to draw a budget constraint, goes through here out to this intercept, and so that budget constraint is generated by a price list P1 hat less than P1 bar, because we can afford more of the first good. The price of the second good is 1 minus this. So now we've kind of constructed these two prices, one price for each of the goods, P1 hat, P2 hat, which generate these two additional hypothetical, if you like, budget constraints. So now we have all the elements in place that we should be able to complete the proof pretty quickly. Actually, let's take this off. We might need this space for something else in just a moment. So let's remove this. And let's start off here by saying, what are these prices, P1 hat, P2 hat, and so on? What are they going to do for us? Well, they're going to define this open set, this neighborhood of P bar. And so let's in fact write that down. Let's say U is, we're defining U to be the set of all price lists in the simplex such that for each component, for each price, Pi is at least as large as Pi hat. And so notice, kind of made that U a little small here, but notice that this is an open set in the simplex because we're looking at prices that with a strict inequality greater than P hat. Also notice that P bar is in the open set because the P hat prices are all less than the P bar prices. So the P bar prices are in here, larger than P hat. So we clearly have an open set containing our benchmark price P bar in its interior, in the U, in the set U. And so now what we have to do is we need to show that for any price list in U that it will be the case that the corresponding budget set will still be a subset of V. So how are we going to do that? Well, geometrically, just notice that any price list now that's in U that does this is going to be a price list that generates a budget constraint that's in between these two orange budget constraints. If we have a price with the first good price larger than P1 hat, then the budget constraint will be steeper than this, And if it's larger than P2 hat, the budget constraint is going to be flatter than this. So we're looking at all the budget constraints that lie in between these two orange budget constraints. And notice that both of the orange budget constraints, the budget sets, the budget constraints lie completely inside the pink bounded region. So all these other budget constraints will as well. So that's really the proof. So let's just write that down. We'll say that if we have a price list in U, then any point that's in the budget set for this price list P, one of these budget sets here, is clearly going to be inside the pink bounded region. And in particular then, it's going to be within epsilon of the P bar budget set. So let's write that down. So we say if we have a point in the budget set for this P, then it's going to be the case that the distance between that point and the budget set for P bar is going to be less than epsilon. And of course, this part here, if the distance between a point and the budget set beta of P bar is less than epsilon, then we're inside the pink bounded region, and in particular, then we're also inside the set V. So this would say that X is therefore also in V. And if we take this whole thing here, then this would say that the budget set at P is a subset of V, because every point in the budget set is in V. And so that really completes the proof, because it's exactly what we wanted to prove, that for any price list in the set U, the corresponding budget set will be a subset of that open set V. Now, that completes the proof for price lists where the prices are all positive, but we now need to check what happens if at least one of the prices is zero. So then the picture looks a little different. Let's draw a diagram for the situation when we have, let's say, P1 bar equal to 0. So the budget constraint then, the budget constraint is going to be a horizontal line, and the budget set will be this set here below the horizontal line, and that budget set is not compact, so we can't apply this theorem to guarantee separation between the budget set and the complement of V, as we did over here. So our V set could look like this, where it might get asymptotically closer to the budget set, and the distance between them then is 0, even though they never actually coincide. So we've got a problem there. So how are we going to deal with that? Let's note one other issue, and that is that we can't define our P1 hat to be something that's less than P1 bar, because P1 bar is already 0. So what we'll do is we will, and I'll use this orange color again, for the prices that are 0, P hat prices that are 0, we'll define the Pi hat to be 0. So we don't have it less than P1 bar, we have it equal. That doesn't change U from being an open set relative to the simplex. That'll still be the case. We'll still have P2 bar, P2 hat, less than P2 bar, but let's see how we're going to construct that P2 hat. So what we'll do to deal with this non-compactness, let's suppose this is the initial bundle, and so we will artificially truncate the budget set at X1 circle here. Here's X2 circle. And So in that truncated part of the budget set to the left of X1 circle, that is compact. It's clearly both closed and bounded. And so again, we can apply the theorem, and the way that's going to look is we'll have an epsilon here. That is, let's make this epsilon here. And that epsilon is less than the distance out to the boundary of V. And so now let's see what happens when we have a budget constraint that comes right out to X2 circle. Let's call that X2 hat as well here. That's how we'll define X2 hat. Just as we did over here, where the budget constraint for P bar intersects the X2 axis. So now our budget constraint that comes out to here is going to look like this. And so this is the budget constraint generated by P2 hat, just like we had over here. And the budget constraint generated by P1 hat, which is equal to P1 bar, which is 0, of course, is this budget constraint here. The same budget constraint as for P bar, of course, because the P1 bar and P1 hat are the same. So I'll draw the corresponding orange budget constraint, which is the same as the green budget constraint here. And so, just like over here, we now have for any price list in the set U, where all the prices are larger than the corresponding PI hats, we're going to have a budget constraint that's in between these two orange budget constraints, just like over here. And so then it is going to be the case that for any bundle, any point in the corresponding budget set for such a price list, that point will be within epsilon of beta of P bar. Over here, it will be within epsilon of beta of P bar because we're down here. And on this side, any such bundle will actually be in the budget set for beta of P bar, so certainly within epsilon. So we have, again, that for any price list in our neighborhood of P bar, U, the budget set will be a subset of the open set V down here. And that completes the proof. So I'll just do this down here. That completes the proof for both price lists where all the prices are positive and for price lists where one or more of the prices is 0. So we've established that the budget set correspondence is upper hemi-continuous. And this lecture is going on a little bit long, so I think what we'll do is we'll take a break here and we'll come back and do a second part of the lecture to show that the budget set correspondence is lower hemi-continuous. So we'll take a break here and then we'll come back.